Okay, so welcome back to Fluid Mechanics Homework number one. This will be part C, and we are beginning on problem statement number one of two for part C. So the problem statement states to derive the basic equation of statics for a fluid of constant density and constant acceleration. For this problem, we will use the variable rho for the density, and we will use the variable g for the gravitational acceleration. So, what is the basic equation of statics for a fluid of constant density and constant acceleration? So if we look at this diagram, and this is a tank filled with a fluid of constant density, and we're trying to get the pressure at a point of, let's say, depth h. The basic equation of statics for a fluid of constant density and constant acceleration allows us to say that the pressure at point h or at depth h would be equal to the density of the liquid times the gravitational constant times h. So, how do we derive this equation? I'm going to scroll down and create another diagram. So here we have another tank filled with a fluid of constant density rho. However, in this tank, we now have a rectangular prism. At depth h, with a differential height of dh and a cross-sectional area of A. So we are working in statics, so the rectangular prism is not moving, and the fluid inside the tank is also not moving. So we do know the fluid is applying pressure forces perpendicular to each of the sides of our rectangular prism. However, since the pressure forces on the side of our rectangular prism are at the same depth, the opposite side of the rectangular prism force will cancel them out. However, the top of our rectangular prism is at a different depth than the bottom of our rectangular prism. So to compensate for this, the force would include the weight of our rectangular prism. So I'm going to write this out. So we have the pressure at H plus dH, which is this point here, times A to get our pressure force, because remember pressure force is pressure times some area, equals the pressure at H times an area plus the weight of our object, which would equal the density, rho, times A times dH times the gravitational constant. Now we notice all three of these terms have A in it, so we can divide by A, which cancels. And simplifying this, we get pH plus dH minus pH all over dH is equal to rho g. Now, we're going to take a look at the up and down scale of our tank, and we're going to label that as Z. And we're going to take positive as upward. So the top of our fluid we're going to take as Z equals 0. Now if we plot out our pressures and Z on an XY plane, so we'll take Z as our x-axis and pressure as our y, and we have the pressure at dH, or sorry, at H plus dH, and we have our pressure at H, and then we have our Z's at H plus dH, but this is negative, remember. because it's below RZ equals 0, and we're taking positive as up, and H, negative H, we can see that there's a negative correlation between the two. So we can rewrite this term as dP over dz, but negative, is equal to rho g. So our next step is to begin integrating this equation. So if we look back at a diagram here, and we have our fluid of constant density, and we're trying to find pressure at this point. The pressure at the top of our fluid at z equals 0 is going to be equal to 0 PA. And at this point, at pressure z, it's going to be equal to negative h. So now we take our integral. I'm going to multiply the dz to the other side. So we get negative, which is a constant on the outside, of the integral dp equal to rho g integral dz. So now we must set up our limits of integration. So for our pressure integral, we'll go from our surface, which is 0, to our pressure at h, dp, which is equal to rho g, and for these limits we'll use negative h and z, because z equals negative h and z equals 0, dz. So then we get pH minus 0 equals rho g from negative h minus 0. I forgot the negative. And multiplying this out and carrying the negative over, we end up getting rho gh, which is the equation, the basic equation of statics for fluid of a constant density and constant acceleration. Okay, so now we're on to the second problem statement of part C, which states use the differential equation from C1 to derive an expression for the force necessary to hold back a wall with W of a rectangular pool of length L with W with a fluid depth of D. So, the differential equation from C1 we got was pressure at some point equals the density of a liquid times the gravitational constant times the height. So, let's draw a diagram of our rectangular pool. So, here's our pool. It has length L with W, and it is filled with fluid with a fluid depth of D. So let's take another diagram and we'll look at the wall that the force is acting on. So we have a pressure force acting against this wall of W. And we're going to take this as Y. So the way we're going to think about doing this, because remember, the pressure force acting on this wall changes according to depth. So the deeper we go, the more pressure will be applied on our wall. So we need to take little cuts all the way down to the bottom of our depth with thickness dy and integrate these and add them all up to get our force. So our force would be equal to P times some area, because remember pressure force is pressure times some area, and our area in this case would be W dy. And in this scenario, I'm going to use y instead of h. So pressure would be equal to rho gy. So we have dF equals to rho gy w dy. Okay, so our next step would be to integrate. So we'll integrate on both sides. And we know that rho and g are constants. And w. Now we got to set our limits of integration. So our limits in this case would be from 0 to d. So we end up getting rho gw times y squared over 2 from 0 to d. And if we plug it back in, we get rho gw d squared over 2.